Right guys, so what we're going to look at in this particular example is how we can write a recurring decimal such as 2.13 in the form P over Q, where P and Q are natural numbers. So we're basically going to write it as a fraction. Okay, so the first thing that we need to do is we need to set this up. So let's have a quick look here. We've got 2.13333333. We're all happy. That's going to continue on forever. Now we're going to try and form a geometric series, and it says an infinite. Okay, so an infinite, remember that s to infinity is equal to a over 1 minus r, where a is your first term, okay, and r is your common ratio. Okay, so that's what we're going to try and find out here. Now hopefully you can see that we can actually break this up, and we can break it up and say, well, we've got 2 plus 1/10, because that there is worth 1/10. And now what we've got here, this is where the geometric sequence starts. Okay, so we're going to break it up and so the first one here, going to the blue, that first 3 here, this first 3, so that was 1/10, this is 3/100ths. So we're going to start with 3/100ths. And then if we go to the next one, this one is tenths, hundredths, thousandths. So what we're going to do then is say, though, that's plus 3/1000ths. And then we've got plus, and if we have a look at the next one, so tenths, hundredths, thousandths, and this is going to be 10,000ths. Okay, so plus 3/10,000, and that's going to carry on forever. So that there, this bit here, guys, is my geometric sequence. So be happy that there is my geometric sequence. Okay, so what we're going to do next is we've got to set up a geometric sequence and find our a, or our first term, which is here, and our r. How do we get from this to this? Okay, so what we have then is this here is my a, so a is equal to 3/100, and my r, in order to get from here to here, what I'm doing is I'm multiplying by 1/10. Okay, so 1/10. From there, guys, all I now need to do is I need to stick that into my formula. On the right hand side, which is up here, I've got my a, I've got my r, and now I'm just going to work out what's going on here. Okay, so let's have a look. We can put s to infinity is equal to my a, which is 3/100, divided by, and it's going to be 1 minus r, so 1 minus 1/10, and you just get your calculator, guys, and you just work that out. If you work that out, it comes out to be 1/30, so the s to infinity here is equal to 1/30, which now means that we have to add that on to the 2 plus the 10th, and we've now got plus 1/30. So all we now need to do is get everything in terms of the same denominator, and then we're finished. We can combine it and get over the form P over Q as requested. Okay, so let's get it all in terms of 30s. So hopefully you can see that this is going to be 60/30. Going to multiply that by 30/30. We need to multiply this one by 3/3, and the other one we can just leave as it is. So we've got 60/30 plus 3/30 plus 1/30. Add all them up, guys, you get 64/30, and you can divide both sides by 2, which gives you 32/15, and we're finished. The next thing we need to do is just put into our calculator 32 divided by 15, press your SD button, and see, does it give you 2.13? And if you put that into your calculator, you'll see that comes out to be 2.13 recurring, which is exactly what it says at the top. Hi guys, so this is the second example for this particular part of the book. says each hour 2.5% of the mass of a radioactive substance present at the beginning of the hour decays. In a lab, an experiment starts with p grams of the substance, and we have to find the expression for the mass that is decayed by the end of the second hour. Okay, so let's have a look at this. So we're using a geometric, and what we have here is the fact that we know that we're looking at the sums. So I'm just going to write down Sn is equal to A1 minus R to the n over 1 minus R, because that's the one that we're going to be using later. Okay, so let's have a quick look, see what it says. It says each hour 2.5% of the mass of a radioactive substance decays. And it starts with p grams of the substance. Okay, so at the end of the first hour, let's have a think what that means. That means if we look at S1, okay, what we're saying here is at the end of the first hour, we're trying to find the expression of the mass that has decayed. So we've got P, and we're saying that 2.5% of that has decayed. Okay, I'm going to put this in fractions if I can, just because it's easier. So 2.5% is equal to 1 over 40. Okay, so what we know is that at the end of the first hour, 1/40th, okay, so 1/40th of P by 1 over 40 has decayed. That's what's asked, the mass that is decayed by the end of the second hour, just done the first hour. Okay, if 1/40th of P has decayed, that means that 39/40ths of P is left. So 1/40th of P has decayed, which means that we have 39/40ths of P left. That's going to be useful for the next one. So let's have a quick look at S2 here. So after S2 is equal to T1 plus T2. Okay. So what we have T1's up here. Let's write that down. So we've got S2 is equal to 1 over 40p, just changed it around there, plus we now need to work out how much has decayed in the second hour. Well, as I said to you before there, guys, if 1/40th of P has decayed here, that means that we have 39/40ths of P that has not decayed. So that would make sense, you know, if this 1/40th of P has decayed, okay, that means that 39/40ths of P has not decayed and is ready again for the next stage. Now, what's going to happen here is this 39/40ths is now, of P is now going to decay, and we're going to lose 1/40th of it because we're going to lose that 2.5% again. So that means of that 39/40ths of P, we are going to get some more decay. So we've got 2.5% of whatever P is, plus now what we have is what was left from the P that did not decay, but now we've got some more decay, which again is multiplied by 1 over 40. I'm just going to rearrange this now, so you can see S2 again is equal to, you can see I can move things around, so it's 140p, I can't do anything with that one, but hopefully you'll see that I can put 140 of P multiplied here by 39 over 40. So this line here, look, is exactly the same as this line here. I've just moved things around. Now hopefully you can see that this is going to give us this is going to carry on in this vein, and you can see that what we've now got is we've got a geometric progression again, where this here is my A, and how are we getting from the first to the second term? Well, we're just multiplying by 39 over 40, so that means that my R is going to be equal to 39 over 40. What we're going to do then is stick it into the formula like before. So we now have S of n is equal to A, which is 1 over 40p, yeah, 1 minus R, which is 39 over 40 to the power of n, don't forget to stick that in the bracket, guys, all over, and it's going to be 1 minus R, which is 1 minus 39 over 40. You're probably in sort of like higher partial credit here, definitely middle. just need to simplify this, and let's just slowly do it. S of n is equal to 1 over 40p. You've got 1 minus 39 over 40n. That's better. Okay, all over. Well, 1 minus 39 over 40 is 1 over 40. You can see here we have 1 over 40 divided by 1 over 40. And 1 over 40 divided by 1 over 40 is just 1. So they'll cancel, or factor I should say. That becomes 1, that becomes 1. And that means now that Sn is equal to P by 1 minus 39 over 40 to the power of n, and we're done. Now you could write that if you wanted to as a decimal, which is P 1 minus 0.975 to the power of n. The two things are exactly the same. Okay, so we need to go to do part I now. I'll do it over here for you guys. And it says find the value of n for which 3/4 of the original mass has decayed. So what we're saying here then is that Sn is equal to 3/4 of P, and we are just going to substitute that in for Sn and then solve. So let's do that. So we've got 3/4 of P is equal to P 1 minus, I'm just keep it in decimal, just easier for this particular one. Okay, n, and you can see here straight away that what we've now got is P, they will cancel, and we now have 3/4 is equal to 1 minus 0.975 to the power of n. Now what we have here, lads, you can see, hopefully you've spotted, that the n's at the top here is a power or an exponent, and that means that in order to do this we're going to have to use logs. That's not the end of the world, we know how to do it. So what we need to do is get everything onto one side and this on the other side. I'm going to take this one across to this side, I'm going to take this across to the other side because I just like it to be positive. So what we now have then is 0.975 to the power of n is equal to, taking this across, so 1 minus 3/4 is 0.25. Okay, so 0.25 or a quarter, depending on what you want to do. I'll leave it in decimals for you guys. And now we've got to undo this log. Okay, so this log here, undo this exponent. Okay, so undo this exponent, and that means we have to take logs. Okay, so take logs both sides. Whatever the base is the log that we're going to do. So here we go, log to the base of 0.975 of 0.975n is equal to log of the base 0.975 and 0.25. And from there, guys, it's just calculator work. We know that all the left hand side is going to collapse down now, and we're going to be left with n, and n is equal to 54.76 to 2 decimal places. Right, try that exercise, guys. Any problems, give me a shout.